Hello, Namaste, Konnichiwa, welcome to Sunny Sensei. In the last few lessons, we learned about polynomials, what polynomials are, how graphs and zeros are connected, and how zeros are related to the coefficients. But now comes the most important part. What kind of questions actually appear in the CBSE board exam? Almost all questions on polynomials follow one of these 7 patterns. We are going to work on questions from all these categories. No made-up questions, no sample questions, only real board exam questions. So let me start with the first category. Type 1 questions focus on the fundamentals of polynomials. Most of these questions are very simple. You can solve many of them in just under a minute. So let us start with the first type 1 question. We have the graph of the polynomial and we have to find the number of zeros. Remember, the zeros of a polynomial are the points where the graph cuts or touches the x-axis. 1, 2, and 3. The graph intersects the x-axis 3 times. This polynomial has 3 zeros. Now let's move to the next question. It's again a graph-based question, very similar to the last one. Pause the video and give it a try. We apply the same idea as before. Here is the x-axis, and here is the graph. The entire graph stays above the x-axis. It never touches the x-axis. There is no intersection with the x-axis. No intersection means no zeros. Option A is our choice. Now let's move to the next question. This one is slightly different. Pause the video and see if you can figure out the number of zeros. The graph cuts the x-axis once on the left side. We have a 0 here. And on the right side, the graph only touches the x-axis at one point. But remember, even touching the x-axis gives us a 0. This polynomial has 2 zeros. Option C is the correct choice. Here is the next one. This time, we have to identify the actual zeros of the polynomial. Pause the video and see if you can find them from the graph. Alright, this is our first 0. The graph touches the x-axis at -2, 0. The 0 of a polynomial is the x value. So we have a 0 at x equals -2. The graph cuts the x-axis again at 2.5, 0. So we have one more 0 at x equals 2.5. Now be careful. This point, 0, 4, is not a 0. Over here, the graph intersects the y-axis, not the x-axis. So the zeros of the polynomial are -2 and 2.5. Option B is the correct choice. Here is another graph-based question. But this time, we have 2 polynomials. Pause the video and give it a try. The 2 graphs intersect the x-axis at the same 2 points. One point on the left side and one more point on the right side. Be careful here. Distinct means we count only unique zeros. Both polynomials have the same 2 zeros. So, the total number of zeros is 4, but the number of distinct zeros is only 2. Option C is our choice. Moving on to the next question. Pause the video and give it a try. We have a polynomial of degree 3. Now remember this rule carefully. a polynomial of degree n can have a maximum of n zeros. So a polynomial of degree 3 can have 0, 1, 2, or even 3 zeros. But it cannot have more than 3 distinct zeros. So option D is the correct choice. Here is the next question. This one is quite simple if you understand how factors and zeros are connected. Pause the video and try solving it yourself. We are given the polynomial p of x equals x minus 2 x plus 3. Now remember, a 0 is the x value for which the polynomial becomes 0. And a polynomial becomes 0 when any one of its factors becomes 0. Our polynomial has two factors, x minus 2 and x plus 3. The factor x minus 2 becomes 0 when x equals 2. The factor x plus 3 becomes 0 when x equals minus 3. Each factor gives us 1 0. So this polynomial has a total of 2 zeros. Option C is the correct choice. Next we have a assertion reason question. Pause the video and give it a try. Alright, let's start with the assertion. It says that the polynomial y square plus 4y plus 3 has 2 zeros. Yes, that's true. This polynomial can be written as y plus 3, y plus 1. Two distinct factors means two distinct zeros. You should figure this out in not more than 10 to 15 seconds. Notice, 3 is 3 times 1 and 4 is 3 plus 1. So, it's quite easy to find the factors. Now let's look at the reason. A quadratic polynomial can have at most 2 zeros. This statement is also true. Both statements are true, but the reason is not the correct explanation of the assertion. Option B is the correct choice. Next, we have another assertion reason question. Please pause the video and give it a try. The assertion says that if the graph of a polynomial touches the x-axis at only one point, then the polynomial cannot be a quadratic polynomial. This statement is false. A quadratic polynomial can have 0, 1, or 2 zeros. So a graph touching the x-axis at one point can still be a quadratic polynomial. Here is an example. A quadratic polynomial with just 1 zero. Now let's look at the reason. A polynomial of degree n can have at most n zeros. This statement is indeed true. The assertion is false, but the reason is true. Option D is our choice. This brings us to the end of Type 1 questions. Let us now move to Type 2. In Type 2 questions, we are given a polynomial and we have to find its zeros, the sum of the zeros or the product of the zeros. With the right approach, you can solve most of these questions in less than a minute. So let's begin with the first Type 2 question. Pause the video and give it a try. Alright. Did you factorize the polynomial to find the zeros? If yes, let me show you a much faster approach. Remember, product of zeros equals C over A. Here, C equals 4 and A equals 1. So the product of the zeros must be 4. Now let's check the options. For option A, 2 times square root 2 is 2 square root 2. Not equal to 4. We drop A. For option B, 2 square root 2 times square root 2 is 4. This looks good. For option C, 4 square root 2 times minus square root 2 equals minus 8, not equal to 4. C is dropped. For option D, square root of 2 times 2 is 2 square root 2. Again, not equal to 4. We drop D. Option B is our choice. Moving on to the next question. As always, take a pause and give it a try. We have a polynomial and we need to find the sum of zeros. As before, no need to find the zeros. Sum of zeros is minus b over a, minus of minus 7 over 5. Minus of minus 7 over 5 is 7 over 5. B is our choice. Just a word of caution, be careful with the sign. Remember, it is minus b over a. Don't forget the minus. Here is another question. Please give it a try. This shouldn't take more than 10 seconds. Alright, to find the answer, we don't have to factor the polynomial. And you don't even have to find the sum or product of the zeros. Look at the polynomial carefully. The constant term is negative. And the coefficient of y square is positive. This means that the product of zeros, c over a, must be negative. And for the product to be negative, one zero must be positive and the other must be negative. Option A, both zeros are negative. Drop it. Option B, both zeros are negative. Drop it. Option C, both zeros are positive. Drop it again. Option D, we have one positive zero and one negative zero. Option D is our choice. Here is the next question. We are given a polynomial and we have to find its zeros. This question is worth 2 marks and you have a minute to solve it. Pause the video and give it a try. Alright, we start with the basics. Zeros are the x values for which px is 0. X square plus 4 by 3x minus 4 by 3 equals 0. Multiply both sides by 3. 3x square plus 4x minus 4 equals 0. Now to factorize this equation, we need two numbers such that product 3 times minus 4 equals minus 12 and sum equals 4. The numbers are 6 and minus 2. We rewrite the equation as 3x square plus 6x minus 2x minus 4 equals 0. We pull out the common factors from the first two and the last two terms. 3x, x plus 2, minus 2, x plus 2 equals 0. Now pull out x plus 2 and we have x plus 2, 3x minus 2 equals 0. We have zeros at x equal to minus 2 and 2 over 3. With this question, we are done with type 2. Now we move one step deeper. In type 3, we will not just find zeros. We will connect zeros with the coefficients of the polynomial. So let's begin type 3 with this question. Take a pause and give it a try. Remember, this question is worth 2 marks and your target is to solve it in under 3 minutes. Alright, this question has 2 parts. Find the zeros and verify the relationship between zeros and the coefficients. To find the zeros, we equate the polynomial to 0. X square plus 7x plus 10 equals 0. To factor, we rewrite this expression as x square plus 2x plus 5x plus 10 equals 0. X is common in the first two terms, and 5 is common in the last two terms. So we have x plus 2 plus 5, x plus 2 equals 0. Now pull out x plus 2 and we have x plus 5, x plus 2 equals 0. X equals minus 5 or minus 2. We call the zeros alpha and beta. We are done with the first step. Now to verify the relationship between zeros and the coefficients, we first compare the given polynomial with the general form of the polynomial. Coefficients are a equals 1, b equals 7, and c equals 10. We will now verify the relationship for the sum of zeros. Alpha plus beta equals minus b over a. The left hand side is alpha plus beta. Alpha is minus 5. Beta is minus 2. Minus 5 plus minus 2 is minus 7, or minus 7 over 1, which is minus b over a. Left hand side equals the right hand side. Now we have alpha times beta equals c over a. The left hand side is alpha times beta. Alpha is minus 5 and beta is minus 2. Minus 5 times minus 2 is 10, or 10 over 1, which is c over a. Left hand side equals the right hand side. Let's now move to the next question. This question looks quite similar to the previous one, but it can be slightly tricky. So take your time, pause the video and give it a try. Alright, we start with the zeros again. X square minus 15 equals 0. X square equals 15, or x equals plus minus square root of 15. Be careful here. Many students forget the negative value. We have two zeros. Alpha equals plus square root 15. Beta equals minus square root 15. Next, we compare the polynomial to the general form of a quadratic polynomial and identify the coefficients. Be careful here as well. There is no x term in x square minus 15. The coefficient of x is 0. So, a equals 1, b equals 0, and c equals minus 15. For verification, we start with alpha plus beta equals minus b over a. The left hand side is alpha plus beta, square root of 15 plus minus square root of 15, which is 0. The right hand side is minus b over a. b equals 0. So, RHS equals 0. The left hand side equals the right hand side. Next we have alpha times beta equals c over a. The left hand side is alpha times beta, square root 15 times minus square root 15. Left hand side equals minus 15. Now, the right hand side is c over a, or minus 15 over 1. We have minus 15. Again, the left hand side equals the right hand side. We are done. This brings us to the end of type 3. Let's now move to type 4. In these questions, the zeros are usually given to us. Using the sum and product of the zeros, we have to evaluate different expressions. Here is our first type 4 question. Alpha and beta are zeros of a polynomial, and our task is to find the value of 1 over alpha plus 1 over beta. Pause the video and give it a try. Alright, did you start by finding the values of alpha and beta? If yes, never do that in the exam. There is another easier and faster approach. We start by finding the sum of zeros. Alpha plus beta equals minus b over a. B is minus 3 and a is 1. So we have minus of minus 3 over 1 or 3. Alpha times beta is c over a. C is minus 1. A is 1. So we have minus 1 over 1 or minus 1. Next, we simplify the expression 1 over alpha plus 1 over beta. LCM of the denominators is alpha times beta. So we have. Now we substitute the values of the sum and product of alpha and beta. The expression equals 3 over minus 1 or minus 3. Here is our next question, similar but slightly more challenging. Pause the video and give it a try. Let me start with a word of caution. We use A, B, C in the general form of the quadratic polynomial. Over here, we have P, Q, and R. Don't get confused. Just map carefully. A equals P, B equals Q, C equals R. Now alpha plus beta is minus b over a or minus q over p. Alpha times beta is c over a or r over p. The expression is alpha cube beta plus beta cube alpha. We pull out the common factor alpha beta, and in the brackets we have alpha square plus beta square. What next? We know the value of alpha beta. But what about alpha square plus beta square? Remember, a plus b whole square equals a square plus b square plus 2ab, or a square plus b square equals a plus b whole square minus 2ab. So we can replace alpha square plus beta square with alpha plus beta whole square minus 2 alpha beta. Now we substitute the values of alpha beta and alpha plus beta. We have we solve further. And we have r q square minus 2rp over p cube. We are done. Here is our next question, quite similar to the previous one. Pause the video and give it a try. We start with the coefficients. A equals 5, B equals minus 16, C equals minus 10. Alpha plus beta is minus b over a or 16 over 5. Alpha times beta is c over a minus 10 over 5 or minus 2. Now the expression is alpha over beta plus beta over alpha. We take the LCM of the denominators, which is alpha beta, and the numerator is alpha square plus beta square. Once again, we use the identity a plus b whole square equals a square plus b square plus 2ab. To replace alpha square plus beta square with alpha plus beta whole square minus 2 alpha beta. Now substitute the values of alpha plus beta and alpha times beta. Solving further, we get minus 7.12. This brings us to the end of type 4. Let's now move to type 5. In these questions, we use the relationship between the zeros and the coefficients to find the missing coefficients of a polynomial. So let's begin with our first type 5 question. This question looks complicated, but it's actually quite simple. Pause the video and give it a try. You have 30 seconds. Alright, we have a polynomial with two zeros, alpha and beta. And we need to find the value of k, the constant term. We start with the given condition. Alpha plus beta plus alpha beta equals minus 2 over 3. Now alpha plus beta is minus b over a. b is 6 and a is 3. So alpha plus beta is minus 6 over 3. Then we have alpha beta, which is c over a. c is k and a is 3. We have k over 3. This equals minus 2 over 3. Every term has a denominator of 3. So we multiply the equation by 3. Minus 6 plus k equals minus 2. K equals minus 2 plus 6 or 4. So the correct choice is option D. Let's move to the next question. This is quite similar to the previous one. Please give it a try. We have a polynomial with two zeros, alpha and beta. And we have to find the value of p. We start with alpha plus beta equals alpha beta. Alpha plus beta is minus b over a. b is minus 2 and a is p. So alpha plus beta is minus of minus 2 over p. Then we have alpha beta, which is c over a. c is 3p. It is not 3. Don't forget the p. a is p. We get 3p over p. p in the denominator cancels out. Minus of minus 2 is 2. So we have 2 equals 3p or p equals 2 over 3. Option B is our choice. Moving further, we have a slightly challenging question. Please pause the video and give it a try. Alright, we always start with the coefficients. A is p, b is minus 14, and c is 8. Next, we'll look at the zeros. We are given that one of the zeros is 6 times the other zero. Alpha equals 6 times beta. We also know alpha plus beta equals minus b over a. Minus of minus 14 over p is 14 over p. We replace alpha with 6 beta. 6 beta plus beta equals 14 over p. 7 beta equals 14 over p, or beta equals 2 over p. alpha times beta is C over A, or 8 over P. Alpha is 6 times beta. So 6 beta times beta equals 8 over P, or 6 beta square equals 8 over P. Now beta equals 2 over P. So P square over P equals 24 over 8, or P equals 3. Here is our next question. This is slightly different, but don't worry, it's not that difficult. Pause the video and give it a try. Alright, zeros are in the ratio 3 over 4. So let the zeros be alpha equals 3k and beta equals 4k, where k is the constant. Notice that when we take the ratio of alpha to beta, k cancels out. We end up with 3 to 4, exactly as given in the question. Now let's identify the coefficients of the polynomial. A is 1, B is A, and C is B. Be extremely careful here. I have intentionally used uppercase A, B, C to avoid confusing these with the lowercase a and b already used in the polynomial. The sum of zeros alpha plus beta equals minus b over a. B, the coefficient of x, is a, and a, the coefficient of x square, is 1. We have minus a over 1. Substituting the value of alpha and beta, 3k plus 4k equals minus a. 7k equals minus a, or k equals minus a over 7. Next, alpha times beta equals c over a. C is lowercase b and a is 1. We have alpha times beta equals b over 1. Substituting values of alpha and beta, we have 3k times 4k equals b. 12k square equals b. Now, using the value of k, 12a square over 49 equals b, or 12a square equals 49b. And with this, we are done with the proof. Now, before we move ahead, look over here. We started by writing the zeros in terms of k. But I suggest that you solve this question once again with a different approach. Start with alpha over beta equals 3 over 4. Which approach do you prefer? Let me know in the comments below. With this, we are done with type 5 questions. Now let's move to type 6. In these questions, the zeros are given to us, and our task is to form the polynomial. So let's begin with our first type 6 question. The zeros are given, and we have to find the polynomial. Pause the video and give it a try. Alright, we have alpha equal to 5 minus 2 square root 3, and beta equals 5 plus 2 square root 3. Now, before I solve this question, let me explain some basics. A quadratic polynomial with zeros alpha and beta can be written as px equals k, x minus alpha, x minus beta. Notice that when x equals alpha, the factor x minus alpha becomes 0. So, p of x becomes 0. Similarly, when x equals beta, the factor x minus beta becomes 0. Again, px becomes 0. This happens regardless of the value of k, as long as k is not 0. Every choice of k gives us a different polynomial. For example, if k equals 1, k equals 2, or k equals 5, we get 3 different polynomials. The polynomials are different, but they all have the same pair of zeros, alpha and beta. Expanding the equation, p of x equals k x square minus alpha x minus beta x plus alpha beta, or p of x equals k times x square minus alpha plus beta x plus alpha beta. Now in most exam questions, you have to find only one, not all possible polynomials. So we usually choose the simplest case, k equals 1. With k equal 1, we get p of x equals x square minus alpha plus beta x plus alpha beta. This is a very useful result. If we know the sum and the product of the zeros, we can easily find the polynomial px using this expression. Don't forget, this polynomial corresponds to a special case where k equals 1. Let's now go back to our question. Alpha plus beta is 5 minus 2 square root 3 plus 5 plus 2 square root 3. Minus 2 square root 3 and plus 2 square root 3 cancel out, and we have 5 plus 5, which is 10. Alpha times beta is 5 minus 2 square root 3, 5 plus 2 square root 3. Now a plus b, a minus b equals a square minus b square. So we get 5 square minus 2 square root 3 whole square. 5 square is 25. 2 square root 3 whole square will be 4 times 3 or 12. 25 minus 12 is 13. Now the polynomial px is x square minus alpha plus beta x plus alpha beta. Substituting values of sum and product of zeros, p of x equals x square minus 10x plus 13. We are done. Now let's move to another question, similar but slightly challenging. Pause the lesson and give it a try. Remember, you have only 60 seconds for this 1-mark question. We have the sum and product of the zeros. So our polynomial px is x square minus alpha plus beta x plus alpha beta. Sum is minus 1 over 3 and product is 2. We have x square minus 1 over 3 x plus 2, or x square plus 1 over 3x plus 2. So our choice is B. No, it's not. Students often make this mistake. Notice the constant term. We need plus 2, but option B has minus 2. B is incorrect. What about the other options? None of them matches px. It's time we go back to the point that I raised earlier. The polynomial here is just one of the polynomials with zeros alpha and beta. To find others, we simply multiply this polynomial by a non-zero constant. Let's multiply px by minus 3 and create one more polynomial, q of x. Q of x is minus 3 times p of x, or qx equals minus 3 times x square plus 1 over 3x plus 2. And we have qx equals minus 3 x square minus x minus 6. D is our choice. Let's now move to the next question. This one is slightly tricky. Please give it a try. Alright, the zeros of the polynomial are given to us. Alpha equals minus 3 and beta equals 8. Our task is to identify the polynomials from these four options. Notice that the options are written in different forms. Option A, C, and D are written in expanded form, while option B is in the factored form. The factored form is usually the easiest place to start with. So we start with option B. And as I explained earlier, we can represent a quadratic polynomial px in its factored form as k x minus alpha x minus beta. We have k x minus alpha is x minus minus 3 or x plus 3. X minus beta is x minus 8. Compare this result with option B carefully. Option B has x plus 3. We can pull out minus 1 from the second factor and we can write it as minus 1 x minus 8. Option B equals minus x plus 3 x minus 8. This matches our expression for k equals minus 1. Option B is our choice. Before we move further, let's have a quick look at the other options too. Remember, we can write a quadratic polynomial in its alternative form. Px equals k x square minus sum of zeros x plus product of zeros. We substitute values of alpha and beta and we have k x square minus 5x minus 24. Now let's compare this with the remaining options. Option A is x square plus 5x minus 4. There is no value of k. That makes option A equals to px. Option A is incorrect. Option C is A, x square plus 5x minus 24. Again, notice the sign of the middle term. It is plus 5, not minus 5. So option C is also incorrect. Finally, option D. X term is missing here. D is also incorrect. Option B is the only correct choice. This was our last type 6 question. Let's now move to type 7. In these questions, we are given a polynomial and its zeros. We have to find another polynomial whose zeros are related to the zeros of the given polynomial. Here is our first type 7 question. This looks challenging, but it's actually quite simple. Please give it a try. Alright, we start with the given polynomial. The sum of zeros, alpha plus beta, is minus coefficient of x, which is q, over coefficient of x square, p. Alpha times beta is constant term 1 over coefficient of x square, which is p. Now, zeros of the second polynomial are 2 over alpha and 2 over beta. One such polynomial can be written as p of x equals x square minus sum of zeros, that is 2 over alpha plus 2 over beta, x plus product of zeros, 2 over alpha times 2 over beta. We have p of x equals x square minus 2. LCM of alpha and beta is alpha beta. We have beta plus alpha in the numerator, x plus 4 over alpha beta. We replace alpha plus beta with minus q over p and alpha beta with 1 over p, and we get the p in the numerator and the denominator of the second term cancels out. We have px equals x square plus 2qx plus 4p. We are done. Here is another very similar question. Apply the same approach as the previous one and try solving it yourself. Alright, for the given polynomial, coefficients are a is 1, b is minus a, and c is minus b. Be very careful here. The easiest way to avoid mistakes is to use uppercase coefficients for the general form of the polynomial. Now alpha plus beta is minus b over a, minus of minus a over 1 or a. Alpha beta is c over a or minus b over 1, which is minus b. Now we have the zeros of the second polynomial, 3 alpha plus 1 and 3 beta plus 1. One such polynomial is p of x equals x square minus sum of zeros, that is 3 alpha plus 1 plus 3 beta plus 1, x, plus product of zeros, 3 alpha plus 1 times 3 beta plus 1. Px equals x square minus 3 alpha plus 3 beta plus 2 x plus 9 alpha beta plus 3 alpha plus 3 beta plus 1. Px equals x square minus 3 alpha plus beta plus 2 x plus 9 alpha beta plus 3 alpha plus beta plus 1. We replace alpha plus beta with a and alpha beta with minus b, and we get px equals x square minus 3a plus 2x plus minus 9b plus 3a plus 1. We are done. Here is our next question. This question is slightly different from the previous ones. Here, we have to first find the zeros of a given polynomial and then use those zeros to find another polynomial. Please pause the video and give it a try. Alright, the polynomial Rx is 4x square plus 3x minus 1. To find zeros, we equate Rx to 0. 4x square plus 3x minus 1 equals 0. To factor, we rewrite as 4x square plus 4x minus x minus 1 equals 0. We pull out 4x from the first two terms. We have 4x, x plus 1. We pull out minus 1 from the last two terms. We have minus x plus 1. And this equals 0. X plus 1 is common in both terms. 4x minus 1, x plus 1 equals 0. Or x equals 1 over 4 or minus 1. We have two zeros. Alpha equals 1 over 4 and beta equals minus 1. Now the zeros of the other polynomial are the reciprocals of these zeros. Zeros are alpha 1 equals 1 over alpha, which is 4. Beta 1 equals 1 over beta, which is minus 1. Now with these zeros, we can make a polynomial. X square minus sum of zeros, x plus the product of zeros. The sum of new zeros is 4 plus minus 1, which is 3. And the product is 4 times minus 1 or minus 4. Therefore, p of x equals x square minus 3x minus 4. And that's the required polynomial. With this, we come to the end of this lesson and also the end of our polynomial series. If you enjoyed this lesson, don't forget to like, share and subscribe to Sunny Sensei. Thank you and see you again soon.